In this section, we're going to learn how to graph rational functions. So let's start by taking a look at all of the different pieces that go into rational functions. First of all, as a reminder, a rational function is when you have a polynomial divided by a polynomial. The domain is where the denominator cannot equal 0. Remember, we can't divide by 0, it's undefined. You have a vertical asymptote where the denominator equals 0. The exception is if you can factor your polynomial function and the denominator cancels, then you will have a hole in the graph instead of an asymptote. Graphing horizontal asymptotes is where it gets a little bit tricky. There's 3 different categories of horizontal asymptotes. The first is if the leading degree in the numerator is smaller than the leading degree in the denominator. The horizontal asymptote will be y equals 0. The way that I remember this rule is by using those parent functions 1 over x or 1 over x squared to remember. Both of those parent functions had a horizontal asymptote at y equals 0. The degree in the numerator is smaller than the degree in the denominator. The second case is when the degree in the numerator equals the degree of the denominator. Then the horizontal asymptote will be the leading coefficient of the numerator divided by the leading coefficient of the denominator. And finally, if the degree of the numerator is greater than the degree of the denominator, there won't be a horizontal asymptote. This leads into the possibility of a slant asymptote. If the degree in the numerator is 1 more than the degree in the denominator, for example, if we had x squared over x, then we would have a slant asymptote. You'll divide the numerator by the denominator and ignore the remainder. The slant asymptote will be a line in the form y equals mx plus b. We won't see slant asymptotes today. That will be the focus of tomorrow's lesson. And finally, a reminder of different types of symmetry. If you substitute negative x into the function and you get back what you started with, it will be symmetric across the y-axis. If you substitute negative x into the function and you get exactly the opposite, it will have symmetry around the origin. We're going to use all of the pieces that we just looked at on our vocab sheet and put those together to graph a rational function. Starting off with domain, our numerator is already factored and nothing cancels, so we set the denominator not equal to 0. 2 ways to solve this one. You can solve by undoing, add the 1 to both sides, and take the square root. However, a lot of you are still forgetting to put the plus or minus on when you take the square root. So the other option is to factor. X squared minus 1 is a difference of squares, so it factors into conjugates. And setting each piece not equal to 0, you're less likely to lose that plus or minus in your domain. Again, because those do not cancel, they are both vertical asymptotes. When you're writing the equation of the asymptote, you have the equal sign, not the not equal to. The not equal to is for the domain restrictions. The equation of the asymptotes would be equal to. For our horizontal or slant asymptotes, the degree in the numerator equals the degree in the denominator. So this is when we take the leading coefficient of the numerator divided by the leading coefficient of the denominator to get our horizontal asymptote. So y equals 2 is the horizontal asymptote of our function. X-intercepts occur when we set the function equal to 0. In this case, if we multiply both sides by the denominator, 0 times x squared minus 1 is still 0. So we really just have to set the numerator equal to 0, dividing by 2, and taking the square root, we get 1 0 of the function at 0, 0. No work to do for our y-intercept. We already know our y-intercept, 0, 0. There can only be one y-intercept. We already found where the graph crosses the y-axis, which is at the origin, so we don't need to substitute 0 in for x and solve on this one. And finally, symmetry, substituting negative x into the function and seeing what happens. Because both of those x's were squared, that negative sign cancels. We get back the same function that we started with. So that means this is an even function or has y-axis symmetry. So any point that we plot on one side of the y-axis, we can reflect over to the other side as well. I'm going to start by sketching the asymptotes, the x-intercepts, and the y-intercept, and using symmetry to see if I can get an idea of what this function looks like as a graph. If that's not enough, I will use a t-chart and plot a few more points. Starting off, we had vertical asymptotes at x equals 1 and x equals -1. We had a horizontal asymptote at y equals 2. And our x and y-intercept were both 0, 0, which is on the y-axis, so I can't reflect it. We don't have any other information about this graph, so I will definitely need to substitute a few values in to see what's going on. Because of the symmetry of this function, I only need to substitute positive or negative values in, and then I can flip them across the y-axis. We already know we can't substitute 1 in, so I'm going to substitute 2, 3, and 4 and see what happens. 2 times 2 squared divided by 2 squared minus 1 gives us 8 divided by 3. 8/3 is approximately 3. It's just a little bit less than 3. Subbing in 3. We have 18 divided by 8. 18/8 simplifies to 9/4, which is 2 1/4. I'm going to graph these 2 points and see if that's not enough with the asymptotes to see what's going on with this graph. We have 2 and 2 2/3, 3, 2 and 1/4. Using the asymptotes, I can get a curve. Flipping those across the y-axis, we have -2, 2 and 2/3, -3, 2 and 1/4. I do want to sub in 1/2 just to see what happens on either side of 0, 0, to see if there's like a W shape in between the two asymptotes or if it's just a parabola, and that horizontal asymptote doesn't affect what happens around 0. Horizontal asymptotes are for as x goes to infinity or x goes to -infinity. So what happens in between the two vertical asymptotes very close to 0, they may not use that horizontal asymptote. So that's why I want to sub in one more value just to check. We have 2 times 1/2 squared over 1/2 squared minus 1. This gives us a value of -2/3. So it looks like this will be a parabola in between those two vertical asymptotes with the vertex at 0, 0.